So, thank you very much for the introduction. Thank you very much for the invitation, and thank you very much for being here at the Tsukuba University to talk today a little bit about the projects on the disposal of high-level radioactive waste in Europe. Before we
Maybe you can.
Yes, okay. So, before we start, I would like to give you a short overview about the classes of radioactive waste we are facing with. And we have here three classes. This is low-level radioactive waste. This means this is waste which are low concentrations and relatively low activities. And we have very low radioactive waste. This is short-lived waste and waste with radionuclides that has short half-lives and very low activities. And you see, with regard to the volume, this is more than 90% of the total waste. The other waste is about 8%, and this comprises on intermediate level waste and high level waste. So we see from the total radioactive waste, only 0.13% is high level radioactive waste. And these data are from 2016. So they might have be a little bit changed, but nevertheless, the proportions remain more or less the same. However, 95% of the waste, of the radioactivity within the waste, is within this intermediate level waste, and in particular with a high level radioactive waste. So this high level radioactive waste is a waste class which requires very intensive and careful awareness. So if we look at the aims of disposal of radioactive waste, I think it's quite clear it should contain the waste, and the waste should be isolated from the accessible biosphere. Should be kept away from humans and from flora and fauna. But also reduce the likelihood of an inadvertent human intrusion into the waste. So, for example, if there's a mining activity for whatever reasons, it should be avoided that because it is no longer known where this waste are, that this waste is touched. We have different disposal options for the radioactive waste. For example, one is the near surface, and one is in deep geological formations. The near surface, this is mainly for short-lived radioactive waste, so it will decay within a limited amount of time. And for low-level waste, also for intermediate level waste. And such disposal sites are already available in many countries. This is an example from Gerhard Proehl in Spain, which is for this short-lived radioactive waste, intermediate and low-level waste. Then the next thing is with the geological formations. In principle, this could be done for all types of waste and disused sources. Disused sources are, for example, small entities which contain a high concentration of radionuclides, which is, for example, used in medicine for treatment or for irradiation of food, which is done in some countries. However, this geological formations is in particular done for high-level waste, and this is for spent nuclear fuel and from waste coming from reprocessing. However, such kind of entities of disposal facilities are not yet available in most countries. So, when we look for the disposal in geological formations, currently we discuss in principle three kinds of host rocks. One host rock is salt, big salt formations, clay formations, or crystalline, or for example, granite. So let's look a little bit more into detail with these salt formations. Salt has very specific characteristics. For example, rock salt behaves elastically under pressure. This means if there are some cracks formed or some holes or fissures, they will, due to the pressure of the overlying rock, they will be filled and closed. And if the cracks do form, they are healed very quickly. This is a big advantage. One other thing is the permeability. The permeability, this means the diffusion, for example, of radionuclides or of material through salt rock is very, very low. And it can be considered nearly impermeable, which ensures the insulation of the waste in the disposal area. High-level radioactive waste produces heat. It produces heat still for a long time because the radionuclides are so much concentrated. By the way, for example, if you go deeper and deeper in the soil or in the earth, it gets warmer and warmer, and part of this energy is due to the radioactive decay from natural radionuclides. So, for salt, the thermal conductivity is higher than for granite or for clay. So this means the radioactive waste can be packed more densely than in clay or granite. The engineering is quite relatively simple because due to the mechanical properties, the construction of large cavities in a salt dome is possible. There's one disadvantage. Salt is also a commodity. We use it in chemical industry, but also in preparation of food. So this means if people in the far future would mine for salt, they could, in principle, approach such a disposal site within a salt formation. This is something which has to be kept in mind. By the way, in Germany, for example, or middle and northern Europe, there are many such salt domes, such salt formations. These salt formations, they were formed about 220 million years ago. At that time, this part of Europe was underwater, and during this time, these salt formations were formed. And they are more or less stable since this time. And if we look for high-level waste, we are looking for necessary isolation periods of up to 1 million of years. So 1 million of years is much less than this 200 million of years, which these formations already exist. Let's have a look at clay. Clay has also some very nice or very good characteristics. It has also some characteristics which are less favorable. For example, clay is impermeable to water. Once the radioactive waste is disposed, it will remain there in the disposal. And the water within the dissolved substances in the rock process are practically immobile. Another thing, you might know that clay has a great sorption capacity for cations. This means cations are sorbed readily. This means that cations, the movement of cations in clay formation would be very, very low. However, we have also some anionic radionuclides, as for example, iodine 129 or technetium 99 or cesium 79. They are anionic and they are not bound by clay. Another good characteristic or feature is that clay is swelling in contact with water. So in contact with water, it absorbs the water and the volume increases. And this means if there are any cracks, the cracks will be sealed quite quickly. However, clay has also a disadvantage. The structure of clay is brittle. It is not very firm. So it is demanding from a structural engineering point of view. So it's more difficult to construct this disposal facility in a clay formation. You need more concrete and things like that. And the other thing is the heat conductivity of clay is low, so you can pack the waste less dense than, for example, as in salt. Another host rock which is worldwide studied is crystalline or granite. Crystalline is a hard rock. And usually it occurs in massive forms. Examples are, for example, in Canada, the Canadian Shield is mainly built of granite, or also Scandinavia and Sweden. This is more or less granite. The permeability of crystalline depends. It is very low if the granite is not fractured. However, granite tends to have some fissures and fractions, and this would then cause a higher permeability and would also enable water to percolate through this granite. This is something which we in principle do not want. And therefore, because in this case, the natural barrier is less effective than in salt or in clay, we have to have more engineered barriers. And in the waste disposal projects so far, dealing with looking for granite, the waste is put into such copper canisters, and these copper canisters are very very carefully welded and then put in the ground. And in addition, an additional barrier is these canisters are surrounded by pentonite to enable the sorption of radionuclides should they be released from this canister. So we need some additional engineered barriers to enable the long-term isolation of the waste. Here, you see a comparison of the three kinds of host rocks. In green, we have the favorable features. In red are the unfavorable features. And yellow is the middle. Not really good, but also not really bad. So you see, all of these different host rocks have advantages and disadvantages. So for the thermal conductivity, salt is quite good. Clay is good and crystalline is medium. The permeability of salt and clay is very low, but it may be high for crystalline if the crystalline is fractured. The firmness is medium for clay and for salt, but very high, of course, for granite. This is a hard rock. The deformation characteristics is positive for salt because it closes cracks immediately because it's creeping. It is closing any fractions. It's medium for clay, but crystalline is quite brittle. It has not such a tendency of self-healing. If you look at the stability of the cavities, which have to be constructed in the deep ground, it is easiest easiest for salt, most complicated for clay and for crystalline medium. The tension in the rock of salt is low because it is creeping to any direction. It is higher in clay and crystalline. Salt has also one disadvantage, and this is that the solubility of salt is very high. If you have an intrusion of water, the cavities will increase relatively quickly. So if water comes in, salt is not a good idea. But the solubility is very low for clay and also for granite. You cannot dissolve clay, and if water comes, it will swell and close any fractions. And also the sorption of radionuclides to salt is very low, whereas it is very high for clay and medium for crystalline. The temperature resistance for salt is high, low for clay, and high for crystalline. So you see, all of these things, all of these host rocks have advantages and disadvantages. And by the end of the day, you have in the construction or in the engineering, these, you have to take credit of the advantages and try to compensate the disadvantages by additional barriers or additional engineering features. Now, let's go to look for some examples of disposal facilities which are planned or under construction. First of all, Finland. I start with Finland because Finland is most advanced in this area. They are already constructing a disposal facility for high-level waste. And they started construction in late 2016. This facility is located near the Baltic coast in the southwest of Finland. The disposal of spent fuel is planned in crystalline rock at a depth of 400 meters. And the waste will be enclosed by copper canisters as we have seen it before. In 2021, Posiva, the Finnish waste management organization, started construction of the first emplacement. And the idea is, or the plan is, to come into operation in the mid-2020s. And this would really be the first operating disposal facility for high-level radioactive waste. There's one other. This is WIP in the United States, but WIP is planned to accept military waste in particular. So this would be really a novelty if this happens. So this waste disposal facility is called Onkalo Disposal Facility for spent fuel. You see, this is built in these big granite cavities. And it consists of an engineered system of different tunnels. And an underground laboratory was set up in Onkalo to study the host rock and also to explore and elaborate the data which are needed to demonstrate safety for this disposal facility. And here you see you have this multi-barrier system for high-level waste. This is a cladding tube, this is a fuel element. They come into this special containment, and this containment comes to in this copper canister. And these copper canisters are welded. They are put in such a cylindrical hole, and then they will be surrounded by bentonite. And then everything is closed and sealed with bentonite. And then this is on the top or on the bottom of the underground. Of this waste disposal facility. So it's a multi-barrier system combining both natural barriers and engineered barriers. And this is the case in all these ideas and concepts for disposal of high-level waste, that you have always a combination of natural and engineered barriers. And as I said, depending on the host rock, the combination of engineered and natural barriers has to be modified accordingly. In France, they plan for a disposal facility for high-level waste in clay. An underground facility, an underground laboratory is in operation since the year 2000 by Andra and UNDRA is a French organization for the management of radioactive waste. And this laboratory is located about 250 kilometers east of Paris. Close to this underground laboratory, there's a potential site for disposal of reprocessing waste, and this is a CGO, which is nearby. And here, the waste will be disposed in a grey rock at a depth of 500 meters. The license application for constructing this disposal facility will be submitted soon. We will see. And the plan is that this disposal facility goes into operation in about 2040. So it's still a long time. In Switzerland, and I heard you will go to Switzerland this year. Switzerland is also quite well advanced. And they plan a disposal facility for low-level waste, for intermediate-level waste, and for high-level waste in clay. In Switzerland, the start of the site selection started in 2008. In the beginning, they looked at both granite and clay. And in 2022, just a few months ago, they have decided that the site for the disposal facility should be in Nördlich-Lägern, this is North Switzerland, close to the border to Germany. And in 2024, this means next year, they want to do a license application at the authorities to get the permission for constructing and for going forward with this project. But nevertheless, it's a long process. In 2034, the construction work for the underground studies will continue, we will start. And in 2045, 20 years from now, more than 20 years from now, there will be a construction of the section for low-level waste and intermediate-level waste. The special thing in Switzerland is they will have a disposal facility for low-level waste and for high-level waste, and for low-level waste and for intermediate-level waste, as well as for high-level waste at the same site. However, there is one section for the intermediate-level waste and the low-level waste, and another section for the high-level waste. So these things are separated. Because for high-level waste, the engineering efforts are more intensive. So in 2050, the idea is to start with the disposal of low-level waste and intermediate-level waste. And in 2055, they will start to construct the section for the high-level waste. In 2060, starting with the disposal of high-level waste, and in 2085, 90, towards the end of the century, they will have this, they intend that this will be closed. So this is really a long, long time, which is needed for such a project. This clay formation in Switzerland, it's called Opalinus clay. And it was formed 175 million years ago. And at that time, northern Switzerland was covered by a shallow sea. And this Opalinus clay is solid, fine mud, of the sediments that were deposited at this time. And the name comes because they found a mollusk in this clay, which is called Necoris opalinum. So this is the name. The name comes from that. So Switzerland is so far quite well advanced with that. The Netherlands. Netherlands is a bit special. The Netherlands have only very little high-level radioactive wastes because they had, I think, 1 or 2 nuclear power plants running. They are meanwhile shut down, and so they don't have too much. So they didn't really know what to do. Maybe they were thinking about to construct new nuclear power plants. So for this time, until they come to a decision, they decided to have an above-ground storage facility in the south of the Netherlands. And this facility is dedicated for long-term interim storage of high-level waste. And so far, it was defined for a storage time of at least 100 years, but it is said it could stay there longer. It was constructed in compliance with very high safety standards, so it can resist fires, can resist earthquakes, explosions, direct aircraft impact, and flooding. It is operated by COVRA. This is a Dutch organization for waste management. And the facility is in operation since 2003. So for that, they have a little bit more time to think about what they do. And hopefully at that time, other countries will have elaborated experience, and then they can possibly follow the experience made in other countries with disposal of high-level radioactive waste. And so the idea is to have a site selection process to start by the end of the century. So this is a long time ago. So it's far ahead. But this is the current idea. You see, these are all projects which take a long time. In Sweden has a similar concept as Finland. However, one must say the Finnish concept started after the Swedish concept, so that's why there are a lot of similarities. Finland is taking already some experience that was made in Sweden. So again, this is Scandinavia. The Scandinavian shield consists mainly of granite. So also in Sweden, the waste will be disposed of in a crystalline rock. The site is about 140 kilometers north of Stockholm, the capital, and it is close to the sea. And at this time, currently, there are also, I think, 2 nuclear power plants are working. A license application has already been started in 2011. The government's assessment is ongoing, or I think it's close to the end meanwhile. But it is a complex issue, and the further questions came up. So additional material was submitted, in particular to see sustainability and the persistence of these copper canisters, because this is a key element of the isolation in disposing waste in granite. The idea now is that the construction of the facility could start in the mid-2020s. By the way, at the same time, a disposal facility in granite is already in operation in 1988, and this is for low-level waste and intermediate-level waste. In Canada is also have a lot of granite. The idea is also to have spent fuel assemblies to be disposed in cheap geological formation. And they have started a site selection process. And one thing is, this selection process is based on voluntary applications of communities. Which have an appropriate geological formation, and those communities could volunteer for hosting this facility. Of course, I mean, when such a project is implemented, there's a lot of investments, a lot of people coming, money comes into this area, and there would be a economic advantage. And though there are now, meanwhile, there are two remaining communities, locations. Both are in East Canada, in the province of Ontario. And one is in sedimentary rock, this is a kind of clay, and Ignatz is crystalline rock. And in 2021, South Bruce site will be further explored by drilling deep boreholes. And the siting decision is expected for 2023. In Germany, the site selection process restarted. It already started in the late 70s. And in the late 70s, a site was selected near Gorleben for disposal of high-level waste in salt rock storage. On-the-ground investigations from 1970 were performed from 1979 to 1999. By the way, in 1999, the Green Party became part of the federal government. It's the first time there could be a connection. Finally, the site was excluded in 2020 because many people were not really happy with it, both for some scientific reasons, but also for non-acceptance of disposal site close to their vicinity in their neighborhood. So a new process started for site selection about 5 years ago. So, and the site selection process started with a wide map of Germany. So starting again from the very beginning. A first interim report was published in 2020 on the first phase of the selection. And this report lists the regions that have already been excluded from the further selection process. And these are in this map, these are the white areas. And it names also those regions that will be examined in more detail during the next phases. So you see, according to this first report, these are the areas that are in principle appropriate to accept high-level radioactive waste from a scientific point of view. And here in the north, we have salt. This is more granite. And here we have some clay, and here's some clay. So we can choose between clay, granite, and salt. So it will be very exciting which of these host rocks by the end will make the race. Originally, this new site selection process was thought to be finished by 2031. Meanwhile, it was said that this process will be delayed at least by another 15 years. So this is 2045, 2050. This is really long-term process. Let's have a look to the United States. I mean, you have been in VIP, in the waste isolation pilot plant, and this is an operation in Carlsbad, New Mexico, since 1999. It was dedicated for military waste, as you know, and it was built in rock salt at a depth of about 650 meters. The closure of VIP is expected around 2050, and the US has several near-surface disposal facilities for low-level waste and for intermediate-level waste. So VIP is for military purposes, and it is not the solution for all the other high-level waste which comes from the nuclear power plants. Already in the last century, a site was characterized and investigated in Yucca Mountain. Yucca Mountain is in Nevada. This is the west of the United States. And Yucca Mountain, you had in the 40s, 50s, and maybe 60s, this Nevada test site where above ground and underground nuclear tests were performed. And the site is within this area. The site is on the top of the mountain, and this is a volcanic ridge in the Nevada test site. And this is about 160 kilometers northwest of Las Vegas. And the host rock is tough. Tough has some permeability, so additional engineered barriers are necessary to guarantee the isolation of the waste. And this Yucca Mountain is made of layers of ashes from volcanic eruptions that happened more than 10 million years ago. And interesting, the site would be about 300 meters below this ridge and about 300 meters above the underlying aquifer. And it's a tunnel system, and this is the entrance to this tunnel where in principle the waste could be disposed of. It is dedicated for about 70,000 tons. The application for licensing is in 2008. Was in 2008. There was in principle, a license is available. However, it has never been implemented, not so far. And very likely, and very likely it will not. But this is not clear. But this is a political process which goes on since for a long time, and no decision has been made yet. The state of Nevada doesn't want it, and the other states also, they don't want it. So we will see what happens with this Yucca Mountain. So we have seen that there is a long way from the concept to start of the disposal. In the case of Switzerland, it is about from 2008 to the end of the century. It's very, very long. So the question is, why does it take so long? First of all, such a disposal system is a very complex system. You have different areas where you have to look at very carefully to demonstrate safety. And by the end of the day, you have to demonstrate safety. This means you have to demonstrate that the biosphere, you have isolation from the biosphere, and should radioactivity come to the biosphere, you should demonstrate compliance with current radiological criteria. This means you have to be sure that also in 10,000 years or 100,000 years, so the people who would live there is not higher than it would be allowed today. And because it is in the very far future, this makes it a bit difficult. And you can, this disposal facility system has more or less three main elements. First is the near field. So, and for the evaluation of the near field, it is necessary to look for the type of waste, what is the origin of the waste, what is the nature of the waste, the quantities and the chemical properties, and also the total inventory. Then for the specific host rock and for the specific condition at the site, you have to develop an engineering system. How needs the waste to be packed? What are the disposal units? How needs the waste to be conditioned? In which form can be put there? And the point is, this has to be done. Such questions have to be decided today. Also, the disposal may occur only in 20, 50 or more years. And then you have also to evaluate both the natural barriers and the engineered barriers, whether you could have an intrusion of water or not. This also takes very long time because, and when you start doing these investigations, you have to build underground laboratories. You have to take samples from the host rock, and you have to investigate whether this formation is homogeneous or not. This is a very long and also expensive studies are necessary to evaluate the near field. So this is in the near field. Okay. Usually, this near field on the disposal site is designed as such that radioactivity will not be released. However, people say, okay, this may happen not now and not in 100 years and not in 1,000 years, but maybe in 10,000 years or in 100,000 years. what is then? And then it's difficult. Then it is said, okay, maybe they build up scenarios saying, okay, when we have something very unexpected, maybe an intrusion of water or any other event, would it be possible that these radionuclides are transported from the near field where it's confined through the host rock to the surface where people live? And to study this, we have to look at the geology, at the hydrogeology, geochemistry. Also, we have to look for tectonic and seismic conditions and for erosion rates. Again, all these investigations have to be performed in a three-dimensional matrix. It is, of course, possible to do such investigations, but it takes time. And sometimes like that, you start with a question, you find the answer for this question, but you find also new question. So you need additional studies. So this makes the thing very long. And the biosphere, of course, then you have to look at the location of the biosphere. Excuse me, it's dry. Dry. You have to look at the climate, the atmosphere, the water bodies, the soils, the topography, the geographic extent, how big is this area, and possible human activities. And you have to look at that not knowing what is in 10,000 years or 100,000 years. So this also takes a lot of considerations and investigations to find a kind of an envelope, to explore the range in which people might be exposed should they live here. So, and you can imagine all these three things, which is a crude simplification, take a lot of time. You cannot start today and be finished tomorrow. This is for next year. What happened now? Okay. And this is the last slide. So, is the question, why do disposal projects for high-level waste need so much time? As I said, the site characterization is time-consuming. You have to develop all these models for the hydrosphere, the geosphere, and the engineering has to be adopted to that. So it requires a comprehensive assessment, which includes all these aspects, to be able to finally demonstrate that the whole system is safe. And to demonstrate the compliance with radiological criteria for up to 1 million years. This is really a challenge. Another aspect is that in general, projects for radioactive waste disposal are very unpopular. People don't like it. People are afraid from radiation. It is as it is. It has many reasons, and it would be another presentation. So there's in many countries, you have a lack of public acceptance in many countries. And a lot of these objections also lead to court cases. People protest and they go to the court. There is such a case may be very long and take years or whatever. And the other thing is also there is some reluctance of politicians to move such projects forward. Because everyone says, okay, yeah, we have to do it in this area. Many people won't like it, and probably this man or woman would not be elected anymore the next time. So there's always some hesitation to push it. There's no hesitation to say the other area in the country could accept it much better. Yeah. Another point is also, I mean, these activities require a very comprehensive evaluation of the license applications. These are piles of documents, or we're filling this room, covering all these different technical aspects. So it's a very complex system to explore the interaction between biosphere, geosphere, and hydrosphere. And sometimes there are simply not enough people who are doing all this work. And this is an additional factor which may delay such projects. And here you have seen, this is an example about the non-acceptance. This is in Switzerland. It says this is atomic garbage disposal, not with us. Or this is here an example from Germany. It says these engineering, these engineering challenges and the challenges to convince people that the disposal of high-level radioactive waste is necessary and has to be done at some point in time. But this is a long process which takes some time, and we have seen some of the countries are already quite well advanced. Other countries will take still some time to at least find an appropriate site. So thank you very much for your attention.